Okay, so in section 4.6, we're going to be looking at resultants now of non-parallel force systems. So the last section, we were looking at forces that would never intersect. Now we have ones that are going in different directions. So the resultant of a non-parallel force system is found essentially the same way process-wise, but we are going to need to resolve at times any non-X or Y forces into their components. So I put a smiley face because you're probably like, well, yeah, that's what we do, right? So there will now be an Rx and an Ry, meaning we're going to have an X component of that resultant and a Y component of that resultant, okay? Now, the process just gets a little bit longer, but again, essentially, we're going to see many of the same parts here. So the first part is going to be the free body diagram and the convention. Then we're going to break the forces into X and Y components if needed. Sometimes we might have our forces all on the X and all on the Y, but if there are any that aren't, then we're going to have to get those components. Then we're going to determine the resultant components and the resultant. So we're first going to sum in our X direction to get the X component of the resultant, then in the Y to get the Y component of the resultant, and then we're going to use those X's and Y's to solve for our resultant, okay, our overall resultant. Then we're going to determine the moment generated by the original individual forces around whatever point on the body we're planning to, whether it's given to us or where we decide. Then we're going to find either our X bar or Y bar. And all that is depending on the direction of the actual distance. So if it's going to be a horizontal distance, it'll be considered an R bar. If it's a vertical distance, if it's a horizontal distance, it's going to be considered an X bar. If it's a vertical distance, it'll be considered a Y bar, okay? So the only reason we call it different is because when we have X and Y components, then there's going to be that difference of it's either going to be along the X or along the Y instead of saying R bar for a radius. Then after we get that, we're going to then determine the final diagram. We're going to draw a final diagram to show, what our answers actually mean. So what we're going to do is we're going to be looking at example 4.5 on pages 72 to 73 in our book. So we're going to use that as our example to kind of test out the process here. And you will find the diagram on page 73, and the problem statement starts on page 72. So it says, determine the resultant of the force system shown in figure 411 and locate the resultant with respect to point A. So going back over here, page 73, here's the illustration that they're referring to, okay? So up here is our original diagram. And what we want to do is we want to find the resultant with respect to that lower left-hand corner where point A is, okay? Now, to kind of expedite this process a little bit, and I know that we know how to do X and Y components. Instead of starting with this diagram here, are you guys comfortable jumping and doing this diagram right here? And I'm going to be like certain that you can find the X and Y components of each one of those forces. You guys feel strong enough to do that at this point? Absolutely. So draw this diagram right here, and we're going to use this then to get our overall moment. So I'm going to keep that there for you, and I'm going to draw it on the side. So I'm going to keep this here so that you can see the values. Again, just to kind of, you would do this on a regular problem, but in order to kind of get to the process, let's just be efficient. And don't forget to add your convention to the top of the problem. Oopsie. Now, once we have our free body diagram all set, okay, then we're going to go to the next page on page 17. And we're gonna skip over 2, okay, because we already did that, broke those forces into X and Y components. But we're gonna be looking at, try to bring this in so that we'll be able to see both. We're gonna be looking at summing the forces to determine those X and Y components of the resultant. So we're gonna sum the forces in the X to get the resultant X component, and then we're gonna sum the forces in the Y to get the resultant Y component. Okay, so sum forces in the X direction equals Rx. So as we look at only horizontal forces, we're gonna have a -6 kips, a positive 14.14 kips, and a positive 24.15 kips, okay? It's gonna be equal to our resultant X component. So our resultant X component, when we add and subtract these, what is our number? Is it positive? 32.29 kips, right? Is equal to Rx, okay? And then our Y is going to be really doing the very same thing, but now we're going to be looking at those vertical forces. So some of our forces in the Y direction is going to be equal to our resultant Y component. So now vertically, we're going to have a positive 10.39. I'm going to put kips down below because I don't have as much room here. Plus 14.14 kips, and then minus 6.47 kips is equal to our resultant Y component. Okay, and our number here, 18.06 kips and it's positive. Yep, RY. There's that one. Okay, so just confirming that we all have the same numbers here. Okay. Now, we want to draw the diagram of the X and Y components to determine the resultant and its direction angle theta, okay? So because both of these are positive, that means we're going to be in the first quadrant. So our X is going to be 32.29 kips to the right, and our Y is going to be 18.06 going up. So I'm going to just kind of shift gears here, and I'm going to draw So go ahead and solve for your resultant using Pythagorean's theorem, but make sure you draw a good diagram here showing those X and Y components. Chris, did you get the X and Y components? I'll kind of show them
I
here.
just got a diagram.
You did? Okay. You feel good about summing in the directions? Okay. Make sure you show your equation in variable form before you put your numbers in. $6.997. I think that's 37, don't you think? 37 kips. There we go. And then our angle. It's gonna be 29.2 degrees. So this is kind of our extra couple steps that we need to take when we're determining the resultant of non-concurrent force systems. We first need to get that X and Y component of the resultant, because now we have forces in both directions, and then find the actual resultant and its angle, theta. Like I said, theta normally from the x-axis to the resultant. So you should be getting 37 kips for the magnitude of that resultant. And then the tangent of 29.2, or I'm sorry, the tangent theta is going to be equal to 29.2 for that theta. Okay. Now we have our resultant determined, but now we've got to figure out, we have to place it in respect to A, but we got to find out where we're going to actually place it. Now I'm going to use their diagram in the book on page 73 to kind of show us, what we're going for here. So on the top of page 73, you're going to notice they have that little illustration of the resultant with the Y component and the X component. And what we want to know is from point A, we're positioning that from point A, how far does that need to be to have the same net effect on the body as these three original forces did? Okay, so we're going to put our finger on A basically, and we want to determine how far that needs to be away. Now, you'll notice here that our resultant, we would have to do that business where we would move it along its line of action, find a perpendicular distance here, and that would be the value. But instead, what we're going to do is we're going to actually use our Y component of that resultant, because it has a perpendicular distance then naturally from A. Now, this is why we don't float components. Do you see it? When we have our resultant here, our point of application, our Y component needs to come from there, and our X also. Don't float them out here or here, because this is not where we want to have our Y component, because it needs to be here so we can measure this distance. Does that make sense to everybody? I know the math teachers will do that floating, and I understand why. But in statics, when we're dealing with forces, we have to know their point of application. And this is where we see that Y component right by where the resultant actually has its application point. We can't float it out here. Same thing with the X. We can't put it up here. It has to be down here along where the application of the start of force R is, that resultant. Okay, most of you have like gotten rid of that bad habit. Okay, and I noticed that on the test, which is good, But here we're seeing why we need to do that. All right, so what we're gonna do to place the X bar, we're gonna be using that RY component, okay? Now, we need to know the total moment though that those separate forces create. So that's gonna be our next step before we can figure out that X bar. So turning over, we're going to determine the moment about point A. We are going to use point A because the problem statement tells us that we're going to. You technically may have a different point you'd be interested in, but for this problem, we're going to use that. So, three-body diagram here. Oopsie. It's over here on back on the bottom of page 16. So we're going to put our finger on A. And we're going to work around and we're going to determine which forces are causing rotation to include in the sum of the moments around a equation. So I'm going to start way over on the left-hand side here and see if we can fit these all in. So sum our moments around A equal to. We're going to put our finger on A. And I'm going to work clockwise around. So I'm going to look at my 6 kips. It is going to cause rotation. So I'm going to take 6 kips times perpendicular distance of 8 feet. And then rotation is going to be counterclockwise. So that's going to be positive out front. Our next one is going to be the 10.39. If we pull in that direction, it doesn't cause rotation because it's going through the point. So we're going to go over to the next corner, 14.14, 14.14. It's going to cause rotation. If we pull it back along its line of action, its perpendicular distance is going to be 10. So 14.14 kips times 10 feet, and it's going to rotate positive. Our next one, here's A, 14.14. Pull in that direction. It's going to also cause rotation. So it's going to be 14.14. We're going to push it back along its line of action. Its perpendicular distance is going to be 8 feet. We're going to rotate in a clockwise direction. So it's going to be negative 14.14 times 8. So that's those two. Then we're going to go down to corner down here, 24.15. It is not going to rotate, so we're not going to include it. It goes right through point A, but the 6.47 does. So 6.47 times perpendicular distance of 10 feet, and it is going to rotate in a negative direction. Bless you. So negative 6.47 kips times 10 feet. Here we go. I just made it. So now we can add and subtract, and we can determine the moment about point A. Somebody gets it, let me know. Say it again. 11.58. Okay, thank you. And it's positive, correct? So kip feet. Great, 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 great. Confirmed. So now we know what the total moment is of the individual forces about point A. And if we go back to that illustration, okay, we're now gonna solve for that X bar, okay, that X bar. So we're gonna set our moment around A equal to our RY component times the X bar. Does everybody see why I'm doing the RY component and not the R? Again, because we need that perpendicular component to point A, okay? So we're gonna say sum our moments around point A is gonna be equal to our resultant Y component times X bar. And it's X bar because we're looking at that horizontal distance. So we know the sum of the moments around A is 1.58 kip feet. It's going to be equal to our RY component, not the resultant, the RY component. So going back over here, 18.06 kips. And then X bar is going to be our unknown. So dividing both sides by 18.06 kips, kips cancel. And what do I get for my distance? 0.64 feet is equal to X bar. This is a final answer. Now we're going to just draw a quick diagram, okay? So our diagram is going to be our rectangle. Here's point A, and our X bar is going to be the distance that we just solved for. 0.64 feet is our X bar. And then we would then show our Y component. This would be our RY. You don't necessarily have to put all the labels, just label them with their variables, RX and then R, which is totally fine. But I want to, just make sure that I know that you know where your resultant would be located using that X bar distance. Does that make sense to everybody? Thank you, Josh. Got the X bar equal to 0.64. Oh, is it meters? No, it's feet. It's feet. I know, we've been flipping back and forth. Sorry, yeah, that's okay. That's okay. We've been flipping back and forth between the kilonewtons and kips and pounds and feet and meters. All right. So how do you guys like that process? Is that okay? Okay, like I said, the bones are similar, right? There's some main components, but then we've got that X and that Y that's in there. All right, let's do another example like this. Instead of doing problem 15 or 415, let's cross this one out and say skip. Okay, let's pick one of our homework problems again. Okay. Let's go back to our homework problems. So our options here are going to be 12 and 16, and those are found on page 74. 12 and 16. So let's go underneath here. So the two that we are picking from are going to be either number 12 here. It says we have a cantilever truss acted on by the forces as shown. Now, again, don't get pulled in by the truss. We're really just looking at these. It's going to be a line from A out to C. And we've got two vertical forces, and then we've got this one at an angle. Okay. So there's that one. And then the other one that we have is going to be number 16 here. And we want to find for each one of these the resultant force that would replace the individual forces. Now, this one, there aren't any forces that are not on the X or Y axis. So you don't have to do components, which is kind of nice. This one, we will have to do components of the one force. So process-wise, the rest of it, the process-wise will be similar. Does anybody have a preference on which one they would rather do, 12 or 16? 12? Okay, Chris says 12. Is anybody opposed? Okay, so we're going to look at 12, okay? Now, 16, like I said, we have these are all on the X and Y axis, and in this one, you're gonna determine the resultant. Locate the resultant with respect to line FJ, meaning pick either F or J to sum your moments around, and that's where your dimension, it's gonna be a Y bar then that's gonna come for that one, okay? So just kind of getting a glimpse at that. But let's do problem 412. And what I'm gonna do is, no, I'll just keep the tape rolling. Otherwise we'll have too many small ones. So I'll keep this up here and I'm gonna grab a piece of paper to draw on. Well, great. Then we get 2 of our homework problems done, right? A little bit less to do. And then we also get familiar with the process in the doing of it. So if we go back to page 16 where we had our process, okay, you're going to notice that the first step was free body diagram and convention. So you want to make sure you have both of those on there. And then the second step is going to be break any forces into their X and Y components that aren't found on the X or Y axis. So I just called this CX and CY because this is coming from point C. So with the 60 degrees and the 4.5 kilonewtons, we're going to break those into their components. So that's going to be a step number 2. We're going to do those components. Okay. So CX is going to be the cosine of 60 times 4.5 kilonewtons. So CX equals, I think 60 cosine is 0.5, right? Yep. So that's going to be 2.25 kilonewtons. And then our CY is going to be the sine of 60 times 4.5 kilonewtons. CY. .897 kilonewtons. Our next step is going to be determining the resultant components and the resultant, okay? So step number 3 is going to be summing our forces in the X to get the X resultant component, and then the summing the forces in the Y to get the Y resultant. So go ahead and do that. And I'll kind of do it in the background here. So sum of the forces in the X is going to be equal to our Rx. And if we look, we only have one X component. So 2.25 kilonewtons is equal to our Rx, okay? Then we're going to sum our forces in the Y direction equal to our Ry component, negative 3 kilonewtons, negative 2.5 kilonewtons, and a negative Cy 3.897 kilonewtons is equal to our Ry component. Did you guys get a negative 9.397 kilonewtons? Awesome. Thank you, James. All right, now we're going to use those to get our resultant. So go ahead if you want. Otherwise, I'll just stick here for just a bit if anybody needs to catch up. But then we're going to use those components to determine our resultant, and make sure that you use that negative Ry that's going down. So we'll be in the 4th quadrant. So you should get a resultant equal to 9.663 kilonewtons. And then the theta coming from the x axis down to our resultant is going to be 76.5 degrees. Okay. Is everybody with me? I'll let anybody who needs to catch up if you need that. Right. All right, so now we have our resultant. We need to locate it along that line. So we want to basically take this and we want to put it up here and we want to position it along this line from A. Like, where would we put it to have the same net effect as these separate forces do? Okay. So as we turn the page now, I'm going to grab a new sheet. We are going to sum our moments around A using these individual forces to determine, what's the rotation that's created by those. Okay. So this is going to be step number 4. Okay. Zoom out just a little bit so we can see. This is going to be sum our moments around A equal to. And we're going to start by putting our finger on A. And we're going to pull in the direction of any of these offset forces. So the first one is 3 kilonewtons. So it's going to be 3 kilonewtons times 3 meters. And it's going to rotate clockwise. So that's going to be negative out front. Then we're going to be 2.5 kilonewtons times 6 meters. And it as well is going to go clockwise. So negative out front of that one as well. And then our last one is going to be our CY component. And the CY component was 3.897 kilonewtons times 9 meters. And it as well is going to rotate clockwise, so negative out front. What about CX? Am I going to worry about CX? No. I'm in moment mode, right? Rotating, and it's not going to create a rotation. It's just going to pull on A, so it's not included. So what is my total moment about point A? It's going to be negative something.
0.073.
59.073 on negative, right? You said a negative 59.073 kilonewton meters. Excellent. Confirmed. Awesome. Thank you. All right. Home stretch. Okay. Now what I like to do is I like to draw my diagram first. So I'm gonna skip over step number 5. We're gonna come back to step number 5. Our step number 6 is going to be drawing our diagram. So what we want to do is we're gonna look at A to C, okay? And we want to position our resultant, okay, here with its X and Y components. Remember correctly. So this was and you don't have to put all the numbers in if you just want to do RX, RY, and then we want to show the resultant in here because we are positioning the resultant, but we're going to be using its Y component. So that is enough. Okay. And then I am going to add my RY component just because I'm going to be using it, right? So that's going to be 9.397. And that's kilonewtons, 9.397 kilonewtons. And to position this along that line AC, this is going to be a horizontal distance. So is this going to be an X bar or a Y bar? Horizontal X bar, exactly. If I would be vertical, I would be Y bar, okay? And when you do the next problem, which was at 16, that will be a Y bar, okay? Because you're going to be going along that height, if you would, of that scaffolding. So this is going to be an X bar. So I'm going to go back up here and we're going to say sum our moment around A is going to be equal to force times distance. Our force is going to be RY. Our distance is going to be X bar. Okay, X bar. We know our sum of our moment around A. We know our y. And don't forget its sign. It's a negative 9.397, okay? We didn't put the negative here because it's pointing down, but we need it in here. And then our only unknown here is going to be our x bar. So negative 59.073 kilonewton meters is equal to Ry, I'm sorry. It's going to be equal to a negative 397? Yeah. Kilonewtons times x bar. So dividing both sides by the negative 9.397 kilonewtons, kilonewtons cancels. Positive, positive. And our x bar is going to be equal to, do we have a number yet? Josh is quick on the calculator. I think William was quick earlier too.
.286.
6.286. And that's going to be meters, right? Put the meters in there. Anybody else get that same number? 6.286 meters. Confirmed? Yep. Okay. Josh said yep. Awesome. And William said yep too. Great. Thank you. So equals 6.286 meters. And there you go. So there's your diagram. So just to review our process, start out with our diagram. Break any forces that aren't on the X and Y axis into their components. Find the Rx, the Ry, and solve for the resultant and its theta. Don't forget it's theta. That's part of the direction. Then we're going to do moments to determine the moments of the individual forces. Then we set those moments equal to. Now, you have to look at which component is perpendicular to the point in the direction you're looking at. The ones we've been doing so far, the two that we did have been X bars. When you do 16, you're doing a Y bar. So it's going to be the X component that you're going to be using multiplied by Y bar. Does that make sense to everybody? Okay. I'll look at that right after this. And then our X bars are only unknown, solve for that. And then we've got a diagram. Always put your diagram. Yes. Oh, did you want to know if I needed a diagram? Always. Oh, you do. I'm so sorry. It's okay. It's okay. So if we look at 416 here, okay, this is the other problem that you're going to do independently. You're going to locate your resultant along this line JF. Okay, that line is vertical instead of horizontal. You're going to have a Y bar distance and you're going to multiply your Y bar. So your sum of your moments, for instance, around J is going to be equal to your Rx component times Y bar. Okay. Because you're going to, you could either do F or J, whichever one you want. Okay. F or J, but it's going to be the Y, it's going to be the X component of that resultant times the Y bar. Because this time it's going to be a vertical distance along that line. Okay. Any questions on that? Great. Great. Let me stop the video here because we're going to switch over to a new last part of our lecture, and it's just a nice breaking point so that we have a separate video.